Hello. Can I just say it's a great honor to be here at this conference, and it was a really exciting for me to read the innovation strategy behind this conference, to see that ambition to put Turkey into the top 10 of countries in the world of GDP by 2023, and to base that on innovation, to base it on R&D, to base it on high-tech exports. It's a terrific vision. So as I say, it's an honor to be here. It's my job for the next 45 minutes, hour or so, to talk about, I think, a parallel strand to that terrific presentation you've just seen by Bertrand Piccard, which I would refer to as blue skies engineering. That's striving, pushing the boundaries of engineering forward and the value that brings. I want to talk about the parallel strand, if you like, blue skies scientific research. And I want to do that by picking out a few of the areas that I think are the most exciting areas in what you might call fundamental science, fundamental physics at the moment. CERN, the Large Hadron Collider, and particle physics, where tremendous strides have been made with the discovery of the Higgs particle. Modern cosmology, and some of the fascinating glimpses we have now into theories that may suggest that there was something before the Big Bang. So the fact that we can make observations that suggest maybe there was a time in the universe before it was hot and dense. And also I want to talk a little bit about astronomy, because it's one of my favorite things. It's one of the things that inspired me into physics when I was young, back in the 1960s and 70s. And the great strides we're making now in exploring the solar system and seeking to answer questions, big questions, such as, are we alone in the universe? So completely blue sky science. I just make one comment on how I think that fits in with the previous talk and with the goal of this conference. I think that this kind of science is the kind of science that inspires the next generation of scientists and engineers. Yes, there are technological spin-offs, and the knowledge can lead you anywhere. 100 years ago, the discovery of the electron led the way for the invention of modern electronics, etc. Blue sky science has always done that. But I think that for me, the value of inspiration in this kind of science, the idea that this is the kind of science that our young children will get interested in and follow through school to university and beyond, is often undervalued. And I see that the mixture of blue skies engineering, blue skies science, education and ambition is the way that you will achieve your goal of moving into the top 10 by 2023, and countries like mine in Britain will continue to excel in science and engineering. So that's the kind of foundation of my talk. I wanted to start, though, I'm talking about blue sky science. What is it? It's almost, in a sense, the most hubristic of human endeavors. The goal, really, in its purest form, is to understand nature, to understand the universe. I thought, well, how can I demonstrate what a terrifically difficult and ambitious goal that is? Well, I thought I'd show you a snapshot of the universe as we see it today. So this video is it's a visualization of data, if you like. So there's a project called the Sloan Digital Sky Survey, whose job it is to plot the coordinates of all the nearby galaxies. And this video is a fly-through of our local piece of the universe. So each one of these almost snowflakes, each one of these sort of dandelion seeds drifting through the blackness is a galaxy, an island of, let's say, 100 billion or more stars like our sun. All of the positions of the nearest galaxies have been measured, and this is a fly-through of that data. So it's real data, a real map of our local universal neighborhood. And you see that it's quite a stunning visualization. We now have measured that in the observable part of the universe, so the bit of the universe we can see, there are of order 350 billion large galaxies. That's 350,000 million galaxies, each with an average 100,000 million stars like our sun. We have strong evidence that the universe extends way beyond the bit we can see. But the goal of fundamental science, the goal of cosmology, is to understand where this came from. And that's difficult. As you can see, the universe is a big place. By the way, we talk about collaboration in innovation, and it's a central part of this conference. That list there was a list of the institutions around the world that participated in gathering this data. So the great challenge of modern cosmology and particle physics at the moment is one of the great challenges is to understand where all that came from. Now, this is a sort of 1 minute history of the universe as we know it at the moment. So the current paradigm is that the universe began 13.798 plus or minus 0.035 billion years ago, one of the great measurements in the history of science, began in a hot, dense state, which we call the Big Bang. And it's been expanding and cooling ever since. And in a sense, the complexity that we see today has crystallized out of that universe as it expanded and cooled. One of the things we've discovered over the last century or so of investigations in fundamental physics is that as you wind time back in the universe from today, 13.8 billion years after it was hot and dense, all the way back to the first billionths of a second after the Big Bang, the universe seems to get simpler and simpler. The complexity melts away, if you like, revealing an underlying simplicity. That's one of the great achievements of 20th century science. This idea that the complexity that we see, the stars, planets, and galaxies, human beings, human civilization, can be understood in terms of a few simple laws and the behavior of a few simple particles. So one way of exploring that idea further, of delving into that paradigm further, is to try and recreate the conditions that were present back at the start of the universe, as close to the Big Bang as we can, and observe them experimentally. See if we can disentangle that underlying simplicity. The place that I've been involved in doing that, and one of, I think, the great scientific achievements of the last few years, is the Large Hadron Collider at CERN, a place where over 80 countries around the world have come together just in the name of blue sky science, for curiosity's sake, exploring the origins of the universe. Your country, Turkey, has been involved at CERN for over 40 years and has recently signed an agreement to take a bigger role in CERN in the future. So there's over 100 Turkish physicists working at the Large Hadron Collider alongside physicists from Europe and Russia and China, the Middle East, America, right across the world. Virtually every country that has any scientific program at all works on this project. This is a picture of the Large Hadron Collider, 27 kilometers in circumference, the largest scientific machine ever built. It sits about 100 meters below the ground on the French-Swiss border. So you can see, actually, to get a sense of scale, that little line, the bright line across the top of this image is Geneva Airport runway. You see Lake Geneva towards the top of the picture. Most of the bottom of the picture, actually, is France. So this is a scientific experiment that spans 2 countries. Its job is to take protons, so the nuclei of hydrogen, the simplest element in the universe, and accelerate them to 99.999999% the speed of light, at which speed they circumnavigate that ring 11,000 times a second. We don't just take one proton and send it one way and one the other way. We compress them into beams, so we have billions of protons orbiting around the ring in 2 beams. They're compressed into something less than the diameter of a human hair, and they're crossed at 4 points on the ring. Each one of those beams carries the energy of an aircraft carrier traveling at 30 miles an hour. And when we collide them together, we can recreate the conditions that were present less than a billionth of a second after the universe began, and we can do that 600 million times a second. So essentially, we're doing experimental physics, but the most extreme experimental physics you could possibly imagine. So that's the Large Hadron Collider. Inside it, by the way, this is a photograph of the LHC when it was being built. So you see a cross-section through the machine itself. So you see those two circles inside that pipe. Those are the so-called beam pipes that carry those beams one way and the other way around the Large Hadron Collider. They're encased in that pipe because they run at 1.9 degrees above absolute zero. So that's less than minus 270 degrees, colder than the space between the stars. The reason for that is that the magnets we need to curve those high-velocity beams around the LHC have to be so powerful that the only way we can build them in any sensible way is to use what's called superconducting magnet technology. So these are wires that have no electrical resistance. This is one of the great industrial spin-offs of CERN, by the way. This is the largest deployment of that kind of technology anywhere in the world. It's the technology you will need if you want to build fusion reactors. It's a technology that would allow you, if you could deploy it in a huge scale, to build maglev trains, etc. So it's the ultimate magnet technology, if you like. One of the great spin-offs, as I say, of this physics is learning how to build those industrial deployments of superconducting magnets. So it's a terrific engineering achievement. We collide those beams together inside 4 detectors, 4 digital cameras, if you like, around the ring. This is the one that I work on, that many Turkish physicists work on. It's called Atlas. It's a 7,000-ton digital camera. And you can perhaps see at the bottom there are some little green blob and little purple blob. I don't know if you can see those guys there. That's a person on this size. So just to get some sense of scale of the Atlas detector. Its job is to take photographs of these collisions, and each layer of the detector is tuned to detect a different kind of subatomic particle that you might make in these collisions. I also show you this diagram because if you can see those ladder-type structures, those gray ladder-type structures, those are also magnets. And to set a sense of scale, I show you a couple of pictures of when the Atlas detector was being built. So that blue circle there, you can see, is the Large Hadron Collider. That's 27 kilometers out around Switzerland and France and back in at the other end. This cavern, bigger than a cathedral, is 100 meters below the ground where Atlas sits. And you see one of those magnets being winched down. This is many years ago now when Atlas was being built. There's another photograph of Atlas almost nearing completion. And you might ask the question, well, why? I thought I'd give you a 2-minute or so introduction to particle physics to tell you why we went to the problem of why did we build a 27-kilometer circumference machine? Why did we build detectors like Atlas? Well, on the eve of the LHC, so before we turned it on, you remember I said that at the start of the universe, we've discovered that the building blocks of reality are very simple. You can write them down on one page of paper, and here they are. These are the elementary particles, the fundamental building blocks of the universe as we knew them on the day we turned on the Large Hadron Collider. You see that there are 12 particles which are called matter particles, of which the first line there are the particles out of which we are made. So to make you, or me, or to make any star or planet or galaxy we can see in the universe, you need 4 particles. You need 2 particles called up and down quarks, which make up protons and neutrons, which make up atomic nuclei. And you need the electrons to go around the up and down quarks to make atoms, bind together to make molecules. And that's it. So you and me are a complex pattern of up and down quarks and electrons stuck together in a rather intricate and interesting way. There's also one other particle in that first row, which has got a funny symbol. It's called a neutrino. It's called an electron neutrino. Those things are fundamental. They're fundamental in the fusion reactions that occur inside the sun. So this is a video image of our sun. You can fit 1 million Earths inside it. It shines by burning 600 million tons of hydrogen into helium every second in its core. Every time hydrogen turns into helium in the core, those strange particles called neutrinos are released, and there are approximately 60,000 million of them passing through every square centimeter of your head every second, now, from the sun. The reason you don't notice that tremendous flux of subatomic particles going through your head is because they don't interact very strongly with normal matter. but they're there and they form a fundamental part of the universe. That seems to be all you need to build a universe, those first 4 particles. But you see, there are 2 other rows of the pink and green particles there. They're called generations or families of particles. They're identical in every way to the first 4, except they're heavier or more massive. Why they exist, we don't know, but we discovered them experimentally over the last few decades. That seems to be a complete set of the matter particles, as far as we can tell. As I say, we don't understand that pattern. It's like the periodic table of the elements. There's something in there. There's a reason for that pattern, but we don't know what it is. The blue particles on the right are the so-called force-carrying particles, and they stick those particles together. 3 fundamental forces are represented here: electromagnetism and the strong and weak nuclear forces. Apart from gravity, which I'll mention a little bit later, that's it. So our fundamental description of the universe and the way it works, apart from the force of gravity, is contained on that one slide. Now, the LHC took that and took the theory, the mathematical theory that describes how those particles work, and looked for a missing link in the theory. Now, I'm going to show you the theory now. It's not supposed to be scary and horrible. It's a relatively simple or complicated piece of mathematics, depending how you look at it. But this is the so-called standard model of particle physics. It was built from really the 1960s onwards on the foundations of quantum theory and relativity, which were written down at the start of the 20th century. And it describes with precision how those particles behave. It passed every experimental test, but it has a separate piece to it. This theory made a prediction from the 1960s, actually, of one more particle that we needed to complete the set. How did it do that? Well, it's interesting. The prediction was inserted for reasons of mathematical elegance, mathematical consistency, if you like, which is a strange concept. There's a physicist called Eugene Wigner who wrote an essay called The Unreasonable Effectiveness of Mathematics in the Physical Sciences. And this is probably the best example of mathematics being unreasonably effective that I can think of. The third line and the fourth lines in that equation deal with something called the Higgs particle, a particle that was predicted, as I said, half a century ago for mathematical reasons. The job of the Higgs is quite simple and quite interesting. The picture is that less than a billionth of a second after the universe began, as the universe expanded and cooled, something condensed out into empty space. So in other words, the theory says that empty space isn't empty. The vacuum of space is not a vacuum, it's not empty. It's filled with something, and that something called the Higgs field, Higgs particles. And the picture, very simply, is that the other particles, so the particles out of which you and me are made, journey through those Higgs particles, which are condensed out into the universe, and by interacting with them, by talking to them, they acquire mass. They get their substance, if you like, from that field. So the reason we are allowed to exist, in the sense that the reason atoms and molecules can form in the universe, is that thing, the Higgs field. A remarkable achievement to predict it, but we looked for 50 years until we turned on the Large Hadron Collider and had never seen it. So it was always possible that this beautiful theoretical construct was wrong. But, as I'm sure you all know, just a few months ago, a few years ago now, we discovered that that theory is true. So this is a picture of the Atlas detector. That's a picture of the Large Hadron Collider, that circle in the background. And I'm going to superimpose this image, which is a life-size photograph taken by Atlas of a series of proton-proton collisions. And that signature is exactly what you would expect if you'd seen a Higgs particle. So we know that that thing exists now. So it's a great achievement When Peter Higgs, by the way, the founder of this theory, got the Nobel Prize last year, he'd waited 50 years for this moment. And I remember watching him in the CERN auditorium when this announcement was made. Professor Higgs, your theory that you worked on all your life, it is right. It's indeed true that empty space isn't empty. It's indeed true that it's filled with particles and your particles are interacting. That's the origin of structures in the universe. And Peter Higgs said, it's very nice to be right sometimes. A very wonderful, understated comment from this great physicist. So that's the state of LHC, the state of particle physics. Just one more comment before I move on to a bit of cosmology and astronomy. This is another picture of Atlas, by the way, and I'm in this one. It's me there with the white hat on. We're talking about innovation. We're talking about spin-offs, talking about knowledge. One of the great spin-offs, technological spin-offs, of which there have been many of the Large Hadron Collider, is, of course, a piece of software, a piece of data manipulation technology and distribution technology, if you like. And I thought I'd show you this document, which is from, you see there's a date on it. It says March 1989. It was a research document written by Tim Berners-Lee at CERN. It's a document to his manager in the IT division. And it says there, it's the Information Management, a proposal. So this is the first proposal for the World Wide Web, that integration of hypertext and transfer protocols and all those things, web browsers, to build the thing that we all know and use today. What I think is wonderful about this is his manager wrote vague but exciting on the top and gave it back to him. But one of the great things about the structure of CERN, the ambition of CERN, is that even though his manager didn't really understand what he was doing, he allowed him to continue. And of course, if you added up how much of the global economy is based on Tim Berners-Lee's work now, then it would have paid for CERN, I suspect, 1,000 times over. Vague, but exciting. Let me move on. So that's the frontier of particle physics at the moment. What about space exploration? Well, you know, at the start of this talk, and I referred back to Bertrand Piccard's wonderful talk about the inspiration of blue skies engineering. Space exploration, this exploration of the universe, I think, for me, is one of the most inspiring things that we do. This is a picture, actually, of a book that I had when I was about 5 years old called The Race into Space. You could collect little cards that told you about space missions out of tea in the UK, very strangely. You bought tea, you got a little card out, you could stick it in a book. And I collected these in 1974. That's me in 1974, by the way. I just thought you might like to know what I looked like then, being inspired by space exploration. The card that inspired me and interested me was this one. It was a proposal back in the early 1970s for a grand tour of the solar system, the Voyager spacecraft. The Voyager spacecraft are marvels of engineering excellence at their best. What was noticed back in the early 70s was that the planets were aligned in such a way that you could send spacecraft out from Earth and visit all the outer gas giants of the solar system. So you could fly past Jupiter, Saturn, and on to Uranus and Neptune in one mission. This alignment wouldn't happen again for 170 years, so there was an imperative to get the engineering right, to get the funding in place, to get the ambition right, to get these little spacecraft built and send them out into space so we could visit the outer gas giants of the solar system. And indeed that was done with Voyager 1 and Voyager 2 launched in the 1970s. Voyager 2 finally reached Neptune in 1989. After a colossally long journey through space. Just to get some sense, this is the older me, but there now for a sense of scale, so there's a reason for this. That's me stood in front of a Voyager spacecraft. So the Voyager spacecraft are no bigger than a reasonably sized car, and they're built with 1960s technology. They have less than 64 kilobytes of memory. Less than 64 kilobytes of memory. And the processing power, well, thousands, tens of thousands times less than an average mobile phone. But they were built and they were sent out. Voyager approached Jupiter in 1978, took this movie, one of the first high-resolution movies of that planet. It flew onto Saturn and made terrific discoveries in Saturn's rings. Saturn's rings are intricate and beautiful structures, 100,000 kilometers across, but only 2 meters thick. So they'd easily fit inside this auditorium, and they're made of pure water ice. Sped on out to Neptune, the icy edge of the solar system, and took this single picture as it went away. It's still the most distant object that humans have made. We're still in touch with it now. It's got a power of 250 watts. It's transmitting back. Light signals take over 18 hours to reach Earth from it. The power of the transmitter is 16 watts, and we're still in contact with that spacecraft. What is that? 30 years after it was launched, over 30 years later. And this is the only picture we have, by the way, of Neptune and its frozen moon, Triton. But the reason I wanted to mention Voyager was that we've been talking, a lot of this, these talks about inspiration and about dreams, about not only about the science, not only about the spin-offs, but about the dreams. Voyager carried a dream, which I think is quite wonderful. It carried on it a message. Because it was known that these spacecraft would head off into interstellar space. Voyager 1, that tiny spacecraft, is now in interstellar space, and it carried this message on it. This is a golden record, which was carried on the side of Voyager, put there at the last minute by NASA in 1977. It contains a map showing where the Earth is, and it contains instructions on how to build a record player. Because, of course, any alien that finds this would have to build a record player in order to play it and decode the messages from Earth. It carries an eclectic mix of music and pictures. It's a strange mixture. These are some of the pictures that were chosen to be on Voyager. I think this central one is particularly odd. It seems to be someone eating a pizza with someone drinking wine from a carafe. I don't know why that was chosen as one of the great messages from Earth, but it was. But also, what was interesting about this record was that it contained messages and music from Earth. It's an encyclopedia, the best we could do on a record to offer a message out to any aliens that might find it. The reason I use that as an introduction is that when Voyager was launched, we had no idea about the probability that there may be other civilizations out there in the universe. We still have no real idea. For all we know, we could be the only civilization, certainly in this local part of the universe. There's no sign of anyone else out there in the Milky Way galaxy, although we've begun to look with radio telescopes. That's interesting. That, I would argue, conveys a great responsibility on us to progress as a civilization, not to do something ridiculous, like destroy ourselves. But what we have done since the 1970s is got closer to answering the question, how many worlds out there might be able to support life? Is there anywhere there that might be able to support a civilization? And there is a spacecraft called the Kepler Space Telescope, which has been answering that question. Kepler does something very simple. What it does is it sits there and looks at stars, one after the other. And what it looks for is a characteristic dip in the brightness of the star, a dip that repeats over and over again. The interpretation of such a dip is that, as you see there, there's a planet passing across the face of a star. Now, as I said, in the 1970s, we had detected no planets beyond our solar system. So although we thought there may be planets out there, it was possible to say, well, no, maybe not. Maybe solar systems are rare. What Kepler has done has found thousands of planets around thousands of stars. The number is of order 2,000 planets now beyond the sun. Including this system, the so-called Kepler-62 system, which has 2 planets which appear to be rocky, Earth-like planets, and orbit at the right distance from a star to support perhaps liquid water on the surface, potential second Earths. This is an artist's impression of what one of those Kepler planets might look like. So now we can do statistics. We can say, in a scientific sense, How unique is the Earth? How many solar systems are out there? How many Earth-like planets might there be out there in the Milky Way? And the number is quite staggering. The number is 20 billion. 20,000 million potentially Earth-like planets out there in the Milky Way. That's about 1 in 10 of the stars in the sky that you can see and that you can't see out to the edge of our galaxy may have a planet that's capable, at least, of supporting life, that's capable, at least, of supporting a civilization. And what I just wanted to say, this is a bit of a look into the future as well, is that we're now at the stage where we can analyze the light from those distant stars as it passes through the atmospheres of those distant planets and look for the composition of the atmospheres. So we can look for signs of oxygen in the atmosphere, which would tell us there was photosynthesis present on that planet. We could even, some optimistic astrophysicists have said, look for signs of industrial pollutants. See, if you looked at our atmosphere from afar, then you would see our civilization. You would see molecules in there that couldn't get there other than through the operation of heavy industry. So it's just possible now that we might be able to detect the presence of life in terms of oxygen, which comes from photosynthesis in an atmosphere, or just possibly on the outside, remote chance, evidence of intelligent life by looking at the atmospheres of distant planets. Very new field in astronomy, but extremely exciting. Now, so I've given 2 examples of experimental physics there. The great technological achievement of the Large Hadron Collider, the discovery of the Higgs particle, a fundamental shift, really, in our understanding of the early universe, and the search for, well, planets beyond the Earth, and possibly the beginnings of a search for extraterrestrial life. There's another way of doing science, which doesn't require big investment, doesn't require big machines, doesn't require spacecraft. It requires just thought. It requires just imagination, a sense of possibility, if you like, and maybe a sprinkling of genius. And I wanted to go back. We're talking about the start of the universe. There's an interesting historical fact about the Big Bang, and that's that it wasn't discovered experimentally first. It was predicted. And it was predicted essentially from the mind, from the work of one physicist, Albert Einstein, one of the great physicists of the late 19th and 20th century. So I thought for just a couple of minutes I'd give you a sense of how that great physicist thought, again with this backdrop of the idea that great ideas don't need to come from huge investment. They need to come from a great education system. They need to come from building an environment where dreamers can dream, where individuals can have wonderful ideas and follow them through. Einstein was fortunate enough to live in such an environment at the turn of the 20th century in Switzerland, and he was able to build a theory which predicted the Big Bang. Now, I want to show you a little video clip because it illustrates beautifully exactly what Einstein was thinking of, which led him to build his theory of gravity, which ultimately leads to a prediction of the origin of the universe. Very simple experiment. I filmed this. I'd like to thank the BBC for allowing me to film it and show it to you today. It's a very simple experiment. Galileo knew about this behavior, this experiment which demonstrates the underlying essence, if you like, of the force of gravity, that one force I didn't talk about when I was talking about particle physics. The experiment is to drop, see how things move in gravitational fields. This experiment is to drop a feather and a bowling ball in a vacuum. So you remove the effects of the air and see the pure effect of gravity. I'll show you what happened. You know what happens, but everyone virtually knows how objects behave in a gravitational field. But when you see it for the first time, it's quite stunning. I should say that this photograph is of a vacuum chamber that NASA own in Ohio. It's the world's biggest vacuum chamber, and you don't usually get a chance to play with these things, but fortunately, myself and NASA and the BBC together managed to play around and drop a feather and a bowling ball in a vacuum. So let me show you what happens. This is in slow motion, feather and a bowling ball falling without the effects of air resistance, so you're seeing the pure effects, the pure behavior of the force of gravity. That's kind of remarkable to see, isn't it? I suppose you knew what was going to happen, which is that when you remove air resistance, things fall at the same rate in a gravitational field. As I said, that's not new. I'll put it on again. It's not new. Galileo knew that. Newton knew that. Einstein's genius was to think about this and say, why? What is my explanation for that? If you look at it again, you can see something interesting. It looks like you could imagine the feathers and the bowling ball are not moving. You could imagine that what's really happening is the ground, the backdrop is moving upwards. The ground is accelerating up to meet them. You could see it that way. Einstein's genius was to say, I think it is that way. I don't think there's a force of gravity pulling those things down towards the ground. I think the feather and the bowling ball in that experiment are staying exactly where you put them. They're just sat there, minding their own business. And what's happening is something interesting is happening to the ground. So Einstein says that the ground is accelerating upwards. Einstein says that what you feel now as you sit on your chair and you think, well, if this guy talks for too much longer, it's going to be quite sore. I want to get up and stretch my legs. What you're feeling, according to Einstein, is the ground accelerating upwards at 9.8 meters per second squared. No such thing, Einstein says, as the force of gravity. Very strange idea. That was back in 1907. He called it the happiest thought of his life. Of course, then what you have to explain is why things orbit. Why does the ground meet the feather and the bowling ball? Why do planets orbit around the sun? Why do galaxies interact with each other in the way that they do? You can't just say that gravity doesn't exist. Well, here is Einstein's genius. Here's what Einstein said. He replaced the force of gravity. So he replaced that idea that there's some force acting between the earth and the bowling balls and the feathers and between you and the earth pulling you together. He replaced it with geometry. Strange thing to do. How can that work? Well, imagine the surface of the earth. This is a good analogy for Einstein's new theory of gravity. So let's say that we stand now, you and a friend, let's say, stand on the equator of the earth next to each other. You stand there, and you agree to walk parallel to your friend up towards the North Pole. We'll walk north. Parallel lines on the surface of the earth are lines of longitude. They meet at the North Pole. So if you didn't know any better, if you thought you were on a completely flat surface, you'd say, well, I don't understand. I'm getting closer to my friend. There must be a force acting between us. There must be a force pulling us together because we bumped into each other at the North Pole. We know different, of course, because we can see that the surface of the earth isn't flat. It is curved. And so that's why we get closer and closer to our friend as we walk up the parallel lines of longitude from the equator to the North Pole. That's what Einstein replaced the force of gravity with. So Einstein's theory is a simple theory to state. Einstein says that matter and energy, you put it in the universe, in space and time, and it curves it. And what you see as an orbit, or the feathers and the bowling ball getting towards the surface of the ground, is simply things moving in straight lines through a curved space. Gravity is kind of an illusion. And he even wrote down an equation. That's my last equation of the night, which says how that happens. The reason I put that up is because equations are interesting things. They're not just mathematics. They tell stories. This equation tells a story. The story is that if you put some kind of distribution of matter onto the left-hand side, let's say a spherical distribution. Let's say we put a star in there. This equation tells you the story of what happens in the vicinity of that bit of matter. So if you go onto the left-hand side, that tells you how that distribution curves the space. That tells you how the planets move. So if you stick a sphere into one side, you get the story of the solar system out the other side, the past, present, and future of the solar system. Einstein's next greatest leap was to take an audacious leap from that equation. He knew that that worked for the solar system. It had been shown that his equations described the orbit of the planet Mercury, for example, better than Newton's did. So he had a good theory. Einstein realized this: why confine myself to the solar system? It's like that great, again, as Bertrand Piccard said, that leap, that tremendous leap. What an audacious thing to do. What if I don't confine that to the solar system, but describe a universe instead? Why can't I use my equation to tell the story of the universe rather than just a solar system? It's roughly the same thing as far as the mathematics go. So he plugged a rough idea of a universe into the right-hand side. This is back in 1915, 1916, way before anybody had measured the way that the galaxies move around. And ultimately, a Belgian priest called Georges Lemaitre did the mathematics. And he sent a letter to Einstein and said, I've just discovered that your equations, your theory of gravity, based on this simple idea of things falling at the same rate in a gravitational field, predicts that there was a day without a yesterday. Einstein's equations predict that you can't have a static universe. The universe is either expanding or contracting. The story these equations tell is that the universe can't be eternal. Essentially, it must have had a beginning. And Lemaitre found this out, and in this poetic language, he said, a day without a yesterday. Einstein said to him, your mathematics is good, but your physics is lousy, because he couldn't believe that his equations were suggesting an origin, a beginning of time. Ultimately, that turned out to be true. Hubble and many other astronomers, shortly after that prediction, made measurements that told them that the galaxies were all flying away from each other, which also suggests that at some time in the past they were closer together. But what I find remarkable about this is that the first prediction of the origin of the universe did not come from big telescopes, did not come from observational astronomy. It came from the minds of a few people who did some mathematics and thought a little bit about very simple things and were led to a description of the universe that, as far as we know to this day, is absolutely accurate. So it's a beautiful story. In the last couple of minutes, I want to get back to that, by the way. I just wanted to make one little deviation to talk a bit about the solar system. And then in the last 5 minutes or so, I want to come back to that idea. The origin of the universe, the Big Bang, a hot, dense start to space and time. Is that right? Well, it turns out possibly that it isn't right, or at least the story is more complicated. But just before I do that, I wanted to show you some of the great pictures from solar system exploration. Remember I said that I thought one of the great questions is, are we alone in the universe? And I mentioned that the Kepler telescope and others are now being able to look at distant planets to see if the atmosphere suggests there might be life. The other great exploration strategy we're pursuing is to physically go to the planets and moons of our solar system. And I think this is one of the tremendously exciting pieces of exploration over the next 10, 15, or 20 years or so. This is a photograph of Mars. And you'll see a little arrow there, which, if you've got very good eyesight, says opportunity. We've got rovers, 2 rovers in particular at the moment on the surface of Mars, trying to characterize the geology and the chemistry of Mars in the hope that we might find perhaps that life existed on Mars or perhaps still exists on Mars. One of them is the Opportunity rover. I show this picture. This is a picture from Martian orbit of a crater called the Victoria crater. If you look at that crater, you'll see the sand dunes in the middle of it. And they're quite a beautiful thing to look at, because if you look at this next picture, that's a picture from the Opportunity rover, which was stood on the rim of that crater looking out across it. So you see the sand dunes there. Opportunity was a small rover. It's functioned for decades. We're still in contact with it now. It's a tremendous piece of engineering again. What it's found, and what the orbiting spacecraft have found, is that Mars is far from the dead world that we thought it was even 15 or 20 years ago. 15 or 20 years ago, it was possible to think of Mars like our moon. Even if it was an interesting planet once, it is no longer an active world. But now we're getting pictures like this back from the space probes that are orbiting and landing on Mars. This is a picture of a crater up towards one of the polar regions of Mars with ice in the floor of the crater. And that is indeed partly water ice. So we know that there's water still present on Mars now, certainly frozen in patches of ice, but possibly liquid under the surface. That's important because everywhere on Earth that we find water, we find life. If there's still liquid water below the surface on Mars, could it be there's life on Mars? That's the question for the next generation of rovers. This is a photograph of the Curiosity rover. When the NASA scientists, Curiosity landed a couple of years ago now, the NASA scientists I spoke to said it behaved like a teenager when it landed because the first thing it did was take a selfie like that. And this is a selfie from Curiosity. So this is Curiosity with its robot arm taking a photograph of itself just after it had landed on the surface of Mars. Curiosity is roving across Mars. It's got a drill. So it's drilling into Martian rocks. This is a recent picture, actually, of Curiosity drilling down. You see that red dust on the surface of Mars is just a sort of a coating. Beneath there, you see this grey-blue basalt rock. And again, Curiosity is finding very strong signs that there was water on Mars in the past, and there may still be water on Mars to this day. So the next generation of spacecraft to Mars, one of them is called ExoMars, the European Space Agency mission, are deliberately designed to go and look for signs of biology on the surface. The ExoMars will land, I think, in 2018. So it's an extremely exciting time. The chance that we might find microbes on Mars is higher now in most people's minds than it's been in 20 or 30 years, perhaps since the time of H.G. Wells. There may be life on Mars after all. What's fascinating, though, is that Mars is not the only place in the solar system, to our surprise, that may harbor life. This is just a picture of the moons, the giant moons of the solar system. You can see their size in relation to Earth, and you can see that many of these moons are planetary-sized bodies with bright, giant, thick atmospheres and perhaps oceans and lakes below the surface. Jupiter has a contingent of moons, which are fascinating active worlds. Before Voyager got there, we thought they might be dead worlds. Now we know they are far from dead. This is a photograph of the moon Io. Io is the most volcanically active place in the solar system, not a dead world at all. Here's a photograph taken of a volcanic eruption from the surface of Io. Io turns itself inside out. Every time we fly past Io, this tiny moon of Jupiter, we see activity has changed the surface beyond all recognition. This was a photograph taken by a video taken by the New Horizons spacecraft, which is going to wake up today, actually. So if you look at the news today, there's a spacecraft on its way out to the outer solar system, which hopefully will be revived from its hibernation today. On its way past Io, it turned its cameras round, and what did it see? A volcanic eruption from the pole of the moon. So Io is a fascinating moon. From the perspective of the question, are we alone, though, this is the most interesting place potentially in the solar system. This is Jupiter's moon Europa, which is an icy surface. You see the cracks in the ice. But what we now know is that below that surface there's an ocean of salt water. There's more water in the oceans of Europa than in all the oceans of the Earth combined. So the next idea from NASA and from the European Space Agency is how can we get down? How can we perhaps probe those oceans? Could there be life in the oceans of Europa? It's entirely possible. And then onwards out to Saturn. Every photograph you show of Saturn is, I think, stunningly beautiful. This is a photograph from the Cassini mission. It looks like a drawing or a painting or a graphic. It's not. It's a photograph of those rings I mentioned earlier. 100,000 kilometers of ice, but 2 meters thick. Delicate interwoven structure in the rings. There's another one. Every photograph you pull out from the Cassini mission is stunning. The planet itself, though, as I mentioned, is perhaps not the most important thing. It's the moons again. This is a very recent picture, released just a month or so ago from Cassini, of the moon Titan. It's a mosaic picture, many images put together. But what you see there is sunlight glinting off lakes. Those are lakes on the surface of Titan. Not lakes of water in this case, lakes of liquid methane. Because Titan is a cold world with a dense atmosphere. But we now strongly believe that there's a water ocean below the surface of Titan in the same way there's an ocean below the surface of Europa. So this is a world with hydrocarbons, with organic molecules, and with liquid water below the surface. Again, potentially, possibly, a home for life. And just one more before I get to the end. This is a photograph of Enceladus, a tiny moon of Saturn. Tiny moon, much smaller than Turkey. You'd fit this moon easily within the country of Turkey. And yet you see that something interesting is happening on this small body's surface. Cassini was instructed to fly through those interesting things. And you see what's happening? There are jets coming up from the surface. Those are jets of liquid water. So they're ice fountains. So we think that there are liquid water lakes again below the surface of this little moon with fountains of ice erupting up. Could there be biological activity in those lakes? Could there be microbes in those jets? We don't know. The next generation of missions to Saturn will be equipped to go and analyze those jets to see what's below the surface of Enceladus. And then before we leave the solar system, I wanted to show you one last picture. This is Voyager's pictures. Voyager 2 is the only spacecraft ever to make it out this far, the frozen edge of the solar system. This is a picture of Neptune, the great outer gas giant. And I wanted to show you this because I mentioned that moons in the solar system, completely unexpected, turned out to be the most interesting objects, the most interesting bodies. Here's Voyager's last picture of Neptune and its frozen moon, Triton. Triton, even though it's frozen, minus 240 degrees on its surface, is not a dead world. It's interesting. Voyager found geysers erupting up from the surface and dropping dark material onto the surface. And this is an artist's impression of what it's thought it would look like if you stood on the surface of this frozen world at the edge of the solar system, Triton, and looked back towards Neptune. So I promised, I hope you agree, that the exploration of the solar system is getting more exciting by the minute, and particularly this idea that we might find life, microbial life, undoubtedly, not complex life, but microbes on these moons or perhaps on the surface of Mars. But I said right at the start of my talk, I would come back to that last question I posed at the start. What about the origin of the universe itself? What do we know about this? Well, this is that picture. I flashed it up quite a few times, this schematic picture of the evolution of the universe. How far back can we see? We can do experiments at the Large Hadron Collider that tell us about stuff that happened less than a billionth of a second after the Big Bang. But we can't see that far. What we can see, though, is the oldest light in the universe, which was released 380,000 years after the Big Bang, not long after. That was the point when atoms formed in the universe for the first time. Before that time, the universe was dense and opaque. Light couldn't travel through it. But 380,000 years after the Big Bang, the universe became cold enough for atoms to form. It became transparent at that point, and that light has been traveling through the universe ever since. Can we see it? Yes, we can, and we've taken a photograph of it. So this is a photograph of the whole sky, which is why it's that shape. It's like a map of the Earth. A photograph of the whole sky of the most ancient light in the universe. It's called the cosmic microwave background radiation. What you're seeing there is the colors represent very slight differences in the temperature of that light. By very slight, I mean the temperature is almost uniform, but it varies at a level of 1 part in 100,000. Those different temperatures correspond to areas of different density in the very early universe. Those areas of different density seeded the formation of the galaxies. So what we're looking at here is the origin of the galaxies and the stars and planets themselves. So it's profoundly important in its own right. This is the origin of structure in the universe. The question then is, what's the origin of these little fluctuations? Where did they come from? And this is where modern physics gets extremely strange and interesting. The theory that best explains those differences in color is called inflationary cosmology. So the idea is that there was a time before the universe got hot and dense, a time before the Big Bang. What seems to have happened is that during that time, the universe was expanding exponentially fast. By exponentially fast, I mean very fast. I mean the observable universe with the 350 billion galaxies that we can see today was at that time way smaller than a single atom. And the universe went from something smaller than an atom to something bigger than the observable universe in less than a millionths of a second. Ridiculous expansion, exponential expansion. Our theory says that before that time, or when the universe was expanding that fast, before the Big Bang, little fluctuations in energy seeded those little variations in density. And they were frozen in by that expansion. And then for some reason, that expansion stopped. And when it stopped, all the energy taken up in that expansion got dumped into space and time. It heated the universe up, and it formed the particles of matter and the energy out of which we are made. So it's a theory of what happened before the Big Bang. It's the only theory we have that fits that data perfectly. So it's almost textbook cosmology. So before the Big Bang, inflationary expansion, it stops, loads of energy get dumped into the universe, it heats up, we measure that as the origin of the universe. But let me leave you with that. That's incredible in itself. And as I say, that theory matches that photograph perfectly well. So that's textbook cosmology. But let me leave you with this, because there's a fascinating twist in that tale. You might say, well, when did that inflation start then? We measured the age of the universe, 13.798 billion years old. That's the time to when the universe was hot. When did this other bit start? Could have been going on for a long time, couldn't it? Well, the answer is yes. We don't know how long that expansion was going on for. And here's the most strange bit of all. All the theories we have, I think that's true to say, all of them, that explain that inflationary expansion suggest something rather strange might have happened. They suggest that the whole thing might not have stopped at once. They suggest that possibly, as the universe was accelerating, the expansion stopped in patches. So you get one little patch that stops, and it heats up, and it makes a universe. And then another bit stops and heats up, and makes a universe. Another bit stops and heats up and makes a universe. And that process may have been going on for a very long time, and may still be going on now. So the picture may be that we are riding on the back of an exponential expansion, a potentiality of creating universes, if you like. And our little bit of space-time is just one of a potentially infinite number of bits of space-time that are riding on this inflationary expansion. There may be an infinite number of universes like ours in what's called an inflationary multiverse. Now, I stress that's the edge of theoretical physics. It does fit the data. It's speculative. It's wonderful. What does it mean? I have no idea. I have no idea what to tell you at all. Could it be that we're a speck in an inflationary multiverse? It's one of the most exciting times, I think, in fundamental physics. Just to summarize, we've just understood this thing about the Higgs particle. It raises very profound questions about the physics of the early universe. We've found out that there are multiple Earth-like planets, billions of them out there in the Milky Way, and we have a way of exploring their atmospheres. We're looking for life on Mars and on the moons of Jupiter and Saturn and beyond. And finally, we have experimental evidence that points us in a new direction in cosmology that's telling us about things that may have happened before what we thought of as the origin of the universe. So with that, the possibilities are wonderful. Thank you for the invitation to talk to you. I've had a wonderful visit to Turkey, and I wish you all the best with the conference. Thank you very much.